The night Titanic sank, the North Atlantic was perfectly calm. No wind, no swell. A surface so still it resembled black glass. Two government inquiries blamed the iceberg, the speed, and the lifeboats. For over a century, that verdict held. But scattered through officer testimony and survivor accounts were details that never added up. Conflicting timelines, a horizon no one could clearly define, and atmospheric conditions so rare they may have rendered the iceberg virtually invisible. What we thought we understood about that night was wrong from the very beginning, and the answer has less to do with human failure than with something no one on that bridge could see. When RMS Titanic set sail in April 1912, the world watched with fascination. Newspapers called it the greatest ship ever built, a floating palace said to be unsinkable. The White Star Line's own brochures boasted of watertight doors and advanced safety features, fueling the belief that disaster was not just unlikely. It was impossible. The phrase "God himself could not sink this ship" appeared in headlines, repeated in drawing rooms and on the docks. Within days of the sinking, the story hardened into legend. Press reports painted a picture of a flawless vessel brought down by a single, fateful encounter with an iceberg. The British and American inquiries echoed this version, placing blame on excessive speed, missed warnings, and a shortage of lifeboats. Witnesses described a calm, starless night and a sudden, unmistakable collision. The official verdicts, splashed across front pages from New York to London, left little room for doubt. Titanic struck an iceberg at high speed, the hull was fatally breached, and the ship went down in less than 3 hours. Images of half-filled lifeboats and the haunting outline of the ship's stern vanishing into the black Atlantic became icons. Survivor accounts, collected by journalists and inquiry clerks, gave rise to enduring tropes, the band playing as the ship listed, officers firing flares into the night, women and children ushered to safety while men stood back. The public narrative settled on a handful of causes: hubris, human error, and the cruel arithmetic of too few lifeboats for too many souls. For decades, this version of events shaped public memory. The Titanic became a cautionary tale about overconfidence and the limits of technology. Inquiry transcripts, press clippings, and survivor interviews formed the backbone of countless books, films, and museum exhibits. The story felt complete, a tragic chain of mistakes, a ship that could not be sunk, and a disaster that seemed, in hindsight, both simple and inevitable. Yet scattered among the official records and newspaper accounts are details that never quite fit, hinting at a deeper, more complicated truth. Inquiry transcripts from 1912 reveal a patchwork of timelines that never quite align. Some survivors insisted the iceberg was sighted minutes before the collision. Others placed the warning and the impact nearly on top of each other. The British and American hearings recorded these contradictions, but the official reports smoothed them over. The result was a tidy narrative, one that left little room for the strange details that crept into sworn testimony. Frederick Fleet, the lookout who first spotted the iceberg, described the sea as flat as glass, a detail echoed by other crew. In most maritime disasters, waves and spray help reveal hazards, catching moonlight or starlight and outlining shapes against the darkness. On Titanic's last night, the absence of wind and ripple erased those clues. Fleet's words, "No break in the water, no sound, just a faint shape," stand at odds with the popular image of a looming white wall. The calm sea paradox, so often mentioned in passing, was quietly set aside in the rush to assign blame. Survivors also disagreed on the sequence of orders from the bridge. Some heard the engines reverse before the turn, others after. Lifeboat launches, recorded in the chaos of the sinking, appear in the logs as neat half-hour intervals, yet personal diaries and wireless messages tell of confusion, missed signals, and boats lowered half-empty. The official timelines, reconstructed from fragments, rarely acknowledge these gaps. For decades, these inconsistencies were dismissed as the fog of disaster. But buried in the inquiry records are hints that something about the environment itself interfered with perception and response. No systematic scientific review followed. Meteorological conditions and optical factors, and the physics of visibility remained on the margins, overshadowed by the simpler story of human error and mechanical fate. The time has come to re-examine those overlooked details. The calm, starless night described in every account may have been more than a backdrop. It may have shaped what the crew could see and how they acted. As new scientific tools allow us to revisit the evidence, the old myths begin to unravel, revealing a more complex and unsettling reality. On the afternoon of April 14, 1912, a powerful Arctic high-pressure cell settled over the North Atlantic, pressing cold, dense air down onto the sea. Barometer readings from ships in the region climbed to nearly 1,035 millibars, an unusually high value for that stretch of ocean. The air was crisp, almost unnaturally clear, with little haze and hardly a breath of wind. But beneath that clarity, the sea itself was changing. Logs from the German steamer Ulster and the British cargo ship Almerian recorded a sharp drop in sea surface temperature, falling from 12.6 degrees Celsius to just above 5 degrees Celsius in a matter of hours. That sudden cooling came as the cold Labrador Current surged beneath the warmer Gulf Stream, creating a steep vertical temperature gradient where the two water masses collided. This contrast set the stage for a rare atmospheric phenomenon. Instead of the usual pattern where air cools as it rises, the surface air over the Grand Banks became colder than the air above. The result was a thermal inversion, a layer of cold, moist air trapped beneath a lid of warmer air, stretching perhaps 150 meters above the waves. Such inversions are known to produce strange optical effects, especially over calm seas. Under these conditions, the boundary between sea and sky can blur, and distant objects may appear distorted, displaced, or even invisible to the human eye. Tim Malton, drawing on ship logs and historical weather charts, traced the outlines of this inversion with unusual precision. The pressure, the temperature drop, the calm, each detail matched the pattern needed for a superior mirage. On Titanic's route, the ocean's surface mirrored the sky, erasing the usual glitter and sparkle that might warn of danger ahead. The ship's officers, relying on experience and the evidence of their senses, believed they were steaming through a clear night. But the environment around them was anything but ordinary. The rare combination of high pressure, rapid cooling, and flat seas created a visual trap, one that would soon confound even the most vigilant lookout. No one on the bridge or in the crow's nest could have known that the very invisible, unstable boundary in the air was producing the clarity they trusted. The night's stillness was not a sign of safety, but the quiet mask of a rare and deceptive phenomenon, one that would soon play a silent role in the unfolding disaster. A layer of cold, dense air hugged the surface of the North Atlantic as Titanic sailed through the night. Above it, a warmer band formed a kind of invisible ceiling, stretching between 50 and 150 meters high. This was a textbook thermal inversion. It is an atmospheric setup where the normal order is flipped. Instead of cooling as you climb, the air actually gets warmer with height. The result is a sharp boundary that bends light in ways the human eye is not built to notice, let alone understand. In these conditions, light rays from distant objects do not travel in straight lines. They curve downward, following the gradient between the cold and warm layers. The math is precise. A refractive index gradient of about 2 millionths per meter, 2 times 10 to the minus 6 per meter, was present that night, enough to shift the image of an object by several degrees as seen from the deck. This is the mechanism behind a superior mirage, a phenomenon mariners sometimes call a fata morgana. Instead of seeing the world as it is, the observer sees a world subtly rearranged by physics. A superior mirage can raise distant ships or icebergs above the horizon, stretch them, or make them seem to hover in the sky. But it can also do the opposite, compressing and dimming objects, blending them into a false horizon. For Titanic's lookouts, the cold layer acted like a lens, lifting light from the iceberg and projecting it higher, even as the base of the berg was masked by a luminous band. The sea and sky blurred together, erasing the sharp contrasts that would normally make ice stand out in the darkness. This was not just an odd trick of the air. The Mirage changed what was visible and what was hidden. Calculations show that the apparent elevation of an iceberg could drop by 5 to 10 degrees, enough to hide its lower half behind a bright haze. The horizon itself became unreliable, a glowing, ambiguous line where the sea ended and the sky began. For the men in the crow's nest, trained to spot danger by silhouette and shadow, the night's clarity was a mirage in more ways than one. The term superior mirage entered the scientific vocabulary long before Titanic's voyage, but few on board would have recognized its signs. On that night, the rare atmospheric setup made the familiar North Atlantic into a hall of mirrors, distorting distances and disguising threats. The physics was invisible, but its consequences were not. The question of what the crew could actually see, what was real and what was a trick of the air, would shape every decision that followed. From the crow's nest, Frederick Fleet and Reginald Lee peered into a night that promised clarity, but delivered only deception. The air was cold and sharp, the sea perfectly still, yet the horizon itself was a lie. Instead of a crisp dividing line, a strange, luminous haze stretched across the water, blending sea and sky into a single, uncertain band. The iceberg, when it finally appeared, did not rise like a mountain from the deep. It materialized as a faint, ghostly shape, its edges blurred and its base swallowed by the false horizon. Fleet described it later as coming out of the haze, a phrase that has puzzled historians for decades. But ray tracing models of that night's atmosphere offer an explanation. The temperature inversion bent light downward, lifting the image of the iceberg and compressing its vertical profile. The result was a hidden lower half, masked by the glowing band that mimicked the true horizon. The upper portion, dimmed and stretched, hovered just above this luminous line, stripped of the sharp contrast that normally signals danger. For the human eye, trained to spot silhouettes against darkness, the effect was almost paralyzing. The iceberg's water-wetted flanks, already dark, merged with the refracted sky. Only at the last moment, when the ship had closed to within a few hundred meters, did the shape break free from the haze, giving the lookouts seconds, not minutes, to react. Calculations based on the ship's speed and the angle of refraction suggest that as much as 30 to 50% of the iceberg's visible mass was lost to this optical trick. At 22 knots, the Titanic covered the final distance in a matter of heartbeats. The lookout's warning was almost simultaneous with the bridge's first glimpse of the danger. In those precious seconds, the difference between detection and collision was erased by a quirk of physics, an invisible boundary in the air, hiding catastrophe in plain sight. This was not a failure of vigilance or technology, but of perception itself. The science of light and air created a world where the familiar rules no longer applied. The men in the crow's nest saw what the environment allowed them to see: an iceberg lifted, dimmed, and nearly erased by the night. The urgency of their warning, the compressed reaction window, and the confusion on the bridge all trace back to this moment, where human senses were quietly outmatched by the invisible forces at work over the North Atlantic. At 23:39 and 30 seconds, Frederick Fleet spotted the iceberg, a faint, uncertain shape on the starboard bow. He rang the warning bell 3 times and shouted down the voice pipe to the bridge. In that instant, the bridge became a crucible of reaction. First Officer William Murdoch, standing watch, heard the alarm and moved to act. The ship's log records the next moments with a precision that strips away the comfort of hindsight. At 23:39 and 31 seconds, the Morse lamp flashed a signal from the bridge, iceberg right ahead. Murdoch ordered the helm hard to starboard and the engines full astern. The quartermaster relayed the command, and the engine telegraph clanged its message down to the machinery spaces below. The sequence that followed was measured in seconds, not minutes. At 23:39 and 33 seconds, the engine room received the order, hard astern. Chief Engineer Thomas Andrews acknowledged the command, and the great turbines began to reverse. By 23:39 and 38 seconds, Marconi operator Jack Phillips tapped out the first CQD distress call, his fingers moving over the wireless set as the ship's fate began to unfold in code. On the bridge, the helm started to respond. The ship's heading shifted, but the change was incremental, a matter of degrees, not salvation. The logs show the steering gear beginning to turn at 23:39 and 46 seconds. Titanic's bow edged away from its original course, but the momentum of 46,000 tons at over 22 knots could not be arrested in an instant. The iceberg, now looming directly in the ship's path, closed the final distance. At 23:40, the collision registered. Officers on the bridge heard the dull, grinding thud as the hull scraped along the submerged ice. The impact was not a single blow, but a series of deep, wrenching noises that traveled through the steel frame, felt by every man on the bridge and below decks. In the space of 30 seconds, the window for action had opened and slammed shut. The compressed timeline, reconstructed from ship logs and officer testimony, reveals a reality far more unforgiving than the tidy legends. Decisions were made in heartbeats, not in the luxury of hindsight. The bridge's response was immediate, but the laws of physics and the ship's own inertia left no room for escape. William Murdoch stood at the center of Titanic's final decision. In the bridge log, his name appears only in passing, but in those seconds, every order and gesture carried the weight of thousands of lives. The familiar story often distills his role to a single command: hard to starboard, engines full astern. Yet the reality is more intricate, shaped by a chain of split-second choices that leave little room for blame or certainty. Testimony from the inquiries shows Murdoch reacting almost as soon as the warning reached the bridge. The gap between Fleet's shout and Murdoch's first order was barely 2 seconds, a span confirmed by both the bridge log and the statements of Quartermaster Hitchens. Murdoch's voice, described as sharp and controlled, cut through the confusion. Helm hard to starboard, engine telegraph to full astern. The commands were relayed down the chain in a matter of heartbeats. The quartermaster spun the wheel, the engine room received the telegraph, and the ship began its slow, reluctant turn. The geometry of the situation left no margin for error. At more than 22 knots, Titanic covered the distance to the iceberg in less than 40 seconds. Murdoch's orders were precise, but the ship's momentum was immense. The rudder could only bite so quickly, and the turbines, designed for steady transatlantic crossings, not emergency reversals, took precious seconds to respond. Officer testimony and modern simulations both confirmed that the helm began to shift within moments, but the change in course was measured in degrees, not in the sweeping arc that might have cleared the danger. Murdoch's decisions have been debated for over a century. Some accounts question whether reversing the engines reduced the rudder's effectiveness, while others point to the compressed timeline and the near-instant response. The evidence from the bridge log and the Morse lamp records shows a man working at the limits of human and mechanical possibility. The environment, distorted by the superior Mirage, the calm sea, and the false horizon, meant that even perfect vigilance could not guarantee escape. In the aftermath, Murdoch's actions were dissected by investigators and historians alike. But the facts remain. The warning came late. The orders were given without hesitation. And the ship's fate was sealed by forces far beyond one officer's control. The nuances of his response, timing, command, and consequence invite a deeper understanding, one that moves beyond blame to the realities of human decision-making under impossible pressure. Titanic's hull stretched 269 meters, engineered for steady passage across the Atlantic. But in the moments before collision, design gave way to the hard limits of physics. The lookout's warning left barely enough time for a single command. Murdoch's orders, hard to starboard and engines reversed, were immediate, but the outcome was already set by geometry and momentum. At 22 knots, Olympic-class liners needed vast space to turn, far more than the few hundred meters that remained. Titanic's turning circle at speed was nearly 1,800 meters. Even with the rudder hard over, the ship's heading shifted at just over 0.03 degrees per second. In the 25 seconds between the helm order and impact, the bow moved less than a degree. With the iceberg only 250 meters ahead, this translated to a lateral shift of just 3.5 meters, scarcely the width of a first-class corridor. The ship's mass, 52,000 tons, brought its own inertia. As Titanic tried to pivot, momentum forced a sideways slide. Naval architects call this added mass, the invisible resistance to sudden change. Calculations show that during the turn, inertia pushed Titanic another 11 meters sideways, compounding the loss of clearance. Combined with the geometric rotation, the total shortfall was 15 meters, the exact margin that might have allowed the hull to clear the ice. Environmental factors offered no reprieve. A binocular misalignment of just 0.03 degrees projected over the closing distance meant a positional error of 13 centimeters. Insignificant alone, but one more link in the chain. The superior Mirage compressed the iceberg's visible profile by up to 15%, making it appear lower and farther than it was. Atmospheric models estimate the visible tip was pushed down by 30 to 40 meters, erasing the final seconds for maneuver. The 2026 Magellan scan confirms the geometry, showing a 12-meter crush zone on the starboard bow, a low-angle gouge along the hull, and a clearance gap that shrank to less than 4 meters before contact. The ship was already turning, but the space was gone. No skill or vigilance could overcome these physical constraints. Disaster and escape were separated by meters, and there were simply too few. Aboard the Californian, just after midnight, the horizon was anything but clear. The ship's log describes a faint, hazy band stretching across the water, blurring the line between sea and sky. Officers on deck watched what appeared to be a large white vessel in the distance, its lights shimmering in the low haze. The air was still, the sea flat, and yet the boundary of the world seemed to float, uncertain and shifting. Crewmen noted the odd brightness along the horizon, an effect later matched by the accounts from Titanic's own lookouts. Rockets arced upward, but their glow was dulled, swallowed by the same luminous haze that had already fooled so many eyes that night. Signals from the Californian's Morse lamp flickered across the water, but the responses, if any, were faint and ambiguous. The white ship in the distance seemed both close and impossibly far, its outline warped by the Mirage. Logs from the Californian record confusion. Was this a liner in trouble, or just another ship out on the open sea? The horizon's haze, shaped by the inversion, distorted not just the view but the very sense of distance, leaving officers to puzzle over a mystery unfolding just beyond their reach. Wireless operators aboard Titanic worked in a constant rhythm of incoming and outgoing messages, their fingers tapping out distress calls into the night. Yet, even as the ship's fate hung in the balance, the logic behind each signal was shaped by what the crew believed they could see and what they could not. The Marconi log records warnings from ships like the Carpathia and Baltic, but the details were vague. Ice was reported, but there were no precise coordinates and no measure of the field's density. Officers on the bridge, reading these messages, weighed the risks through a lens distorted by the night's deceptive clarity. No course change was ordered after the last warning. The sea ahead still seemed open, the horizon unbroken. As the iceberg struck, Jack Phillips sent the first CQD, then SOS, his transmissions echoing through the ether. But the window for outside help was already closing. The Californian, only 20 miles away, received the faint signals but failed to grasp their urgency. Its crew, peering into the same luminous haze, misread the Titanic's rockets as routine flares. The official inquiries later scrutinized every wireless entry and every decision made in those final hours. The record shows a chain of signals, each one shaped by uncertainty, each one narrowing the chance for rescue until it was gone. The 2022 Magellan expedition brought the wreck of Titanic into unprecedented clarity. Using a full-hull digital scan, researchers mapped the starboard breach with a precision that leaves no room for myth. The opening stretches 6 meters long and 2 meters high, a wound not of gaping holes but of metal peeled and buckled along a jagged path. The breach begins just forward of the boiler rooms and runs aft along the hull, tracing the iceberg's glancing blow. Instead of a single catastrophic tear, the point cloud data reveals a series of overlapping deformations, plates bent inward, seams splayed, and rivet lines disrupted in a pattern that matches the iceberg's low scraping contact. The geometry of the damage is unmistakable. The opening follows the path of the ship's starboard bulkhead, slicing through compartments that were supposed to contain flooding. The hull plates, each nearly 1 inch thick, show signs of progressive failure, edges curled back, steel fractured along lines of stress. The scan allows investigators to measure the breach's area, roughly 12 square meters, with a total affected zone of over 167 square meters when accounting for adjacent buckling and compromised seams. This is not the cartoonish gash of early newspaper illustrations, but a complex, multi-stage failure mapped down to the centimeter. The breach's precise shape explains the rapid sequence of flooding. Water entered through the initial opening and raced along the bulkhead, overwhelming the forward compartments in minutes. The Magellan scan's point cloud even captures the subtle distortions where the hull began to ripple under pressure, evidence of material fatigue and the immense forces at work. The digital autopsy transforms the abstract idea of hull breach into something tangible, a measured physical reality that rewrites what was long assumed about Titanic's final hours. The data shows not just where the ship was struck, but how the damage spread, setting the stage for the catastrophic material failures that would follow. The steel plates that formed Titanic's hull were held together by more than 3 million rivets, each one driven by hand or hydraulic press, at the Harland and Wolff Yard in Belfast. Metallurgical analysis of rivets recovered from the wreck tells a different story than the one promised in the shipyard's ledgers. Tensile tests show a 40% reduction in shear strength compared to what was specified at launch. Under magnification, the iron is riddled with slag inclusions and brittle seams, the result of cost-saving choices and rushed wartime supply chains. These weaknesses were not theoretical. When the iceberg scraped along the starboard bow, the impact forced a shockwave through the hull. Plates that should have flexed instead tore at the seams. Hundreds of rivet holes show elongation and microcracking, evidence that the hull's longitudinal strength was already compromised before the collision. The 2022 Magellan scan maps the breach with a precision that leaves no room for speculation. The opening is not a single gash, but a jagged path, 6 meters long, 2 meters high, with adjacent buckling spreading over more than 160 square meters. The pattern matches the path of the iceberg's glancing blow, but the speed of failure is what stands out. Computational fluid dynamics models, using the real breach geometry and the measured rivet strength, reveal a flood progression that moves faster than any contemporary estimate. Water poured into the forward compartments, overwhelming bulkheads that were supposed to contain it. The flood advanced in a cascade, each failed seam accelerating the next. Titanic sank in 2 hours and 45 minutes, far faster than the 3.5 hours predicted by her designers. When simulations restore the rivets to their intended strength, the sinking slows by nearly half an hour. That missing time is not just a technicality. It was the window for launching lifeboats, for sending distress calls, for hope. The Magellan dataset draws a direct line from microscopic flaws in the iron to the scale and speed of the disaster. The ship's fate was sealed not only by what was seen on the surface, but by what was hidden deep within the metal itself. History resists simplicity. Even a century later, the cold data beneath the Atlantic unsettles what we think we know. New scans and forensic studies reveal how easily perception, then and now, can distort reality. As technology sharpens our view, old myths fracture, but but unanswered questions remain. In the search for truth, every detail matters, and the danger of certainty endures. What else in our history waits, silent and unseen, for us to finally look closer? Share your thoughts below.